Hello everybody, welcome to our channel NCERT Science. I know how stressful it is to prepare for board exams, so I am here to make it fun and easy for you to learn the concepts. As you know, there are 15 chapters in NCERT Science for Class 9, and I will be explaining one chapter per video to make the concept easy and understandable for you. These videos will also be helpful for those preparing for NTSE and NEET or JEE. So let's jump right in and start with chapter 1, Matter in Our Surroundings. So I'm going to present on Microsoft Whiteboard, and I took pictures from NCERT textbook that I found online. So we are going to be doing chemistry, matter in our surroundings. Alright, let's get started. So, this is just a basic overview of what we already know about atoms, molecules, and about chemistry. So this is like how it originated. Here we have the introduction, and here we have Panch Tattva. According to Indian philosophers, they called matter Panch Tattva. And then around the same time, there were ancient Greek philosophers who also began classifying matter. And now we're progressing more in this field, and we're conducting experiments, researches, everything to get to know more about what constitutes everything around us. So the first important concept we're going to be touching is physical nature of matter. So first of all, if we know how matter looks, and to get a basic idea of how it looks and what to imagine when somebody says matter or something. So matter is said once every minute maybe in chemistry lectures. So if you want to imagine something for matter, you need to know the physical nature. So the first point is that it is made up of particles. So it might seem obvious. You might say, obviously it's made of particles, but for them, for Indian philosophers or Greek philosophers back then, it was not obvious. It was the greatest discovery of that time. So matter is made up of particles, and this can be proven using this little experiment here, in which you take a beaker of water. Again, beaker is another term that you see very often in chemistry, and almost every experiment has a beaker in it. So let's just take water, another common compound. So once we take water and we add salt, so that's H2O, and that's NaCl, and you add salt. So particles of water, let me switch colors, react with particles of salt, and then it forms salt solution, right? So it has particles of salt attached to particles of water, and it produces the salty taste to water whenever you drink it or use it. So now we have a question that says, how small are these particles of matter? Let me tell you, they are very, very, very small. Can you believe it? If I say there's particles of matter all around you right now in the air, yes, you can, because you're a chemistry student. But for them, for ancient philosophers, this was a great thing too. So there are very, very, very small particles of matter, and this can be proven using the potassium permanganate experiment. So basically this experiment will show how the particles of matter react and how small they actually are. So this is a pretty important concept. So explaining the experiment. So you have one beaker and you have water in it. You add potassium permanganate crystals, so it turns a shade of pink. Now, I don't have many shades of pink to show you, but I'm going to represent it using intensity for this experiment. So it's deep pink. And now you take a second beaker. So this is like step 1. Step 2, you take a second beaker, you add one part of this into water again. Okay, so this one already has a few. So one crystal, say you just dropped one crystal of potassium permanganate. One crystal has many particles in it. So the many particles get dissolved in water, and so you take a fraction of this one crystal, which means you're taking a fraction of the many particles that are present in this one crystal. So that gives you pink again, but it gives you a lesser intensity pink. And then you take a fraction of that again into the third beaker. So this is step 3. And there's already water in that again, but this time there's little less intensity, and it keeps going like that until it's almost pure. It looks almost like pure water. It doesn't look like it has a hint of potassium permanganate in it at all. It looks almost colorless. I can't say completely colorless, because there will still be a few particles of potassium permanganate in the water, but it won't show so much, right? So this shows that there are many particles of matter, and they're so small that even if you take, like, if there's 20 ml in the first 20 ml of water in the first beaker, and you add one crystal, and you take 1 ml of this 20 ml, that's really small. That's a really small amount. And you take 1 ml and add it to the already present 19 ml, let's say. So that's a very small, 1 ml is a very small amount of 20 ml. And so this gets diluted, and it keeps getting diluted until it doesn't show much at all. This experiment proves that there are very small particles of potassium permanganate in one crystal. Imagine if you have a handful of crystals and you put it in water. That's not what we're talking about now. We're talking about one tiny crystal about this size. Can't say exactly if it's this size, but it's very, very small. Alright, so that shows how potassium permanganate. So this is a very famous experiment, and this is commonly called the potassium permanganate experiment. So I'm going to write it here, potassium permanganate experiment. I'm so sorry. So, like I said, the potassium permanganate experiment is very famous in NCERT 9th, and this is because it shows how small the particles of matter are. Alright, so once we're good with that, we'll move on to the second characteristic part of the particles of matter. So this is the second one. Particles of matter have spaces between them. So in general, these spaces are called interstitial spaces. Interstitial spaces. Alright, so based on whether the particles of matter are atoms or molecules, they're called interatomic particles or intermolecular spaces. I think we're most familiar with intermolecular spaces, but on a more general note, this is called interstitial spaces. So this is general, and we're most familiar with this. Alright, so let's imagine a solid. So it has these spaces, these particles of matter, and they're very tightly packed. So this is a solid. And then we have a liquid. So in a liquid, even if you take the same space, even if you take the same sized container, the particles of liquid are a little far away. They're not as packed as the particles of solids. And then when you take a gas, even if it's the same sized container, they're very far apart. And this shows us that they have, and when you find, when you're trying to find the spaces between these particles, you can see that the space between here, the space between here, and the space between these two particles, these two particles, these two particles, and these two particles, they're very different. And the space here is nothing compared to the space that's here. So these spaces are really present there. Even if not this big, there are spaces. No matter how tightly they're packed, no matter how tightly the particles of a solid are packed, they do have spaces between them. They might be very, very negligibly small, but there still are spaces present there. For gases, it is a little more. We still can't see matter, we still can't see any particles of matter, but relative to their size, particles of gases have the maximum interstitial spaces. So I'm going to keep saying interstitial spaces because this is more general. So now you don't know whether I'm talking about an atom, a molecule, a compound, or anything now, because I am just taking a hypothetical example. So I am going to say in general, this is interstitial spaces. If I talk about water molecules, then I'm going to say the intermolecular spaces in water. For liquids, that's relatively more than solids but less than gases. And if I take gold, which is an element, so it's one atom that we're talking about, I'm going to say the interatomic spaces in gold, in between the particles of gold, is very negligible compared to that of gases. Alright, so we have, I lost it, okay. So now we have these experiments. Nope, doesn't want to cooperate with me. Alright, let us cooperate with it. Okay, so you have a few activities here. One thing I like about NCERT is that they make it very interactive. So you can go through these activities by yourself, and most of these activities are things that you can try at home if you have the right material, so you can observe it for yourself and see how it is, and see whether chemistry works out the way the authors of books really say it works out. Alright, so that was the second part. That was the second point. The first point was that particles of matter has many particles of matter. The second one was that the particles of matter have spaces between them. Now this is the third part. So particles of matter attract each other. So this again, on a more general note, this is called interstitial forces of attraction. I am going, throughout the lessons, I am going to keep throwing in a few extra points, because if you're writing your board exams, your teachers, whoever is going to correct them, will be impressed that you know something other than what's in the textbook, and you might get awarded more points because of that. Or if you're preparing for NTSE or NEET or JEE, points like this will come in handy for you. Alright, so particles of matter attract each other. So it depends. One thing you're supposed to know about interstitial forces of attraction is that it depends on interstitial spaces. It is inversely proportional to interstitial spaces. Okay, so And this relation, I'm going to say interstitial forces of attraction, is inversely proportional to interstitial spaces. And that is because if you take the situation of solids, liquids, and gases again, so if there are particles that are packed, like in solids, the forces of attraction will be much more, because there's not much space that you can move to lose that attraction. But if you move to liquids, they're a little more far apart, so they have to move a little more before they attract each other, and in that movement they lose their attractive force. Not so much, but they still do lose a little, and they lose more than solids, liquids, and gases. And gases are very far away, so they have minimum forces of attraction. They have gases have maximum interstitial spaces, but they have minimum interstitial forces of attraction. Similarly, solids have maximum interstitial forces of attraction because they have minimum interstitial spaces. So those are the two ways of saying it. This is occurring because of the occurrence of this, or this is occurring because of an occurrence in this. That's two ways you can put it. So this is another activity that may help you remember. So you can ask a few friends to stand together holding each other by the hands, by the shoulders first, by the hands next, and by the fingers in the third group. So I'm bad at drawing. So when they're touching by their fingers, they have very little forces of attraction. But then when they're touching with their hands, they have a little more. This is group 2, this is group 3, and this is group 1, let's say. And they are very close together, group 1. Group 2 is a little more closer together, but group 3 is the farthest away. So if you ask another person to come running into them, they won't move so easily because they have much more attraction between them. They might move, but they won't move as easily as they will move because they're just touching by their fingers. So even when you push their hands away, they will break. Their chain will break. But even if their chain won't break until you run into them. This shows that as interstitial spaces decrease, interstitial forces of attraction increase. And that's what carries to this as well. As interstitial spaces increase, interstitial forces of attraction decrease. And that's all there is in this experiment. You can try this, you can have fun, you can remember. This is a very fun way of remembering the relation between interstitial spaces and interstitial forces of attraction. Okay, so again, as I said, I'm not going through these activities because they just prove whatever has been discussed here, and you can try this at home and you can discuss this with your friends and see if they got the same results as you did, and that's another fun way of learning. And then we have a few questions which we will discuss now. Which of the following are matter? Chair. So chair is an example of matter because chair has particles of matter that is made up of, if it's a plastic chair, it has particles of plastic in it. It is made up of particles of plastic. If it's a wooden chair, it's made up of particles of wood. Whatever it is made up of something. And matter is defined, so this is an important definition. Let me not write it here because it's important. Alright, so let me move here and right here. Matter is anything, so this is a very basic, the most simplest definition you can ever have for matter. Anything that occupies space and has mass. or you can also say anything that has space and volume, because whatever occupies space has volume. So anything that has mass and volume, or anything that occupies space and has mass, this is matter. This is a very important definition of matter, and this definition will come in handy when you're deciding what is matter. In questions like this definition will come in handy. So according to this definition, chair occupies space, chair has a mass. So chair is an example of matter. Air occupies space. If you put air in a container and you weigh it based on, so if you take a container and you create vacuum in it where there's no air, and you weigh and you put it on the balance for weighing it, maybe it's 20 grams, and then you fill air with it and you put it on the scale again, it might be 22 grams. So it has mass and it occupied space in the container. So air is matter. Love, you cannot measure, you can't see if love occupies space. You don't know if love has mass. So this is not an example of matter. I will cross it out with blue. Smell does not occupy space. Smell does not have mass. So that is not an example of matter. Hate, no, that's an emotion. You can't measure hate based on how much space it occupies or how much mass it has. Hate, smell, love, they're emotions and they're senses. They're not examples of matter. Almonds, yes they are, because you can say give me 2 kgs of almonds, or fill this whole box with almonds. So the almonds is an example of matter. Thought, again, you can't say I have 2 kgs of thought with me, or you can't say I have a box full of thoughts with me. You can't say that. Even if you say that, that might come as a metaphor, but it's not real. You can't say give me a box of thought. You can't go to a shop and say that. So this is not an example of matter. Cold, you can't say give me a bottle full of cold. Although this is very helpful in summer, you can't say that. So this is not an example of matter. Lemon, yes, you can say give me 10 lemons, or you can say give me a whole pack of lemons. So this is an example of matter. It has mass. You can say give me 200 grams of lemons. Yes, so lemon is an example of matter. Water is an example of matter, like we were discussing with solids, liquids, and gases. Water is probably the most common state of matter or example of matter we always discuss in chemistry. And obviously it's made up, the earth is made up of 72%, so it's probably the most common example of matter as well. Smell of perfume, yes it is. There might be a little confusion based on this, but the smell of perfume, when you release perfume into a closed bottle per se, it smells very strongly. But when you release it into a room, it doesn't smell as strong, but you can still smell it because it's distributed all across the room. It occupies space, although it doesn't have mass, or it might, yeah, it doesn't have mass, but it occupies the space, be it in the bottle or in the room, it occupies space. So the smell of perfume is an example of matter. So next question, give reasons for the following observation. The smell of hot, sizzling food reaches you several meters away, but to get to that smell from cold food, you have to go close. So one property of heat is that it is light. So hot particles of air are lighter than colder particles of air. So I'm going to write here, air that is hot is lighter than the air that is cold. So the hot air rises up in atmosphere. If this is atmosphere, this is hot air, and below hot air we have cold air. So hot air travels faster and it travels greater distances. So whenever at home you have something cooking in the microwave, even though you're in another room, you'll come and say, hey, what's cooking? But then if something is in the fridge and you just take it out, you can't smell it from that far away. You actually have to be there until you smell it and you can say, oh, I want to eat this too. So that is the reason for that. A diver is able to cut through water in a swimming pool. With what property of matter does this observation show? And then the next one is, what are the characteristics of the particles of matter? So I did these two. Try this one on your own, and this we just discussed all over throughout this video until now. This is what we discussed, so you should be able to answer this. Alright, moving on. States of matter. So I'm pretty sure we've been studying the states of matter since a long time. If not in such a depth, we have a basic understanding about what the three basic states of matter: solid, liquid, gas. I mentioned it even previously in the video. So the first one is solid state, the second one is the liquid state, and then we have the gaseous state. These three are the basic three states of matter. So solid, liquid, and gases. So whenever we see around us, like if you have a table in front of you, that is a solid. If you have a bottle which has water in it, water is a liquid, and with the air that you're breathing in right now, those are gases. The air is an example of gas. So wherever you look around you, these three basic states of matter are visible, unless you're in a swimming pool where there's just liquid. But right now, sitting wherever you're sitting, on a chair, on the bed, listening to me, you can see all three states of matter around you. That's why there are the three basic states of matter. So we'll study about the properties of each one, and we'll know how to differentiate between solid, liquid, and gases. This is pretty simple because we've been doing this since a long time, but I just want to go through very quickly and see. So here they gave a few examples of solids: a pen, a book, a needle, a piece of wooden stick. And all these are examples of solids. You can, they have a definite shape, they have distinct boundaries. Your pen is not flowing anywhere. You can hold it in your hand, you can set it on the table. It's not, when you put it on the table, it's not going to float away, or it's not going to flow like water. It has a fixed volume. If you drop it into a beaker containing water, the water level will rise up because the pen has a fixed volume. Even if you drop it in another beaker containing water, the water level will rise by the same level. This shows that solids have fixed volumes. So if they're hammered, pulled, or dropped, if they're hammered, they're likely to break. If it's a pen, or if it's a wooden stick, or if it's if it's a book, it won't break. But if it's pulled, the book might tear if you pull it really hard from both sides. And if it is dropped, the piece might break, the piece of wooden stick might break, the pen might break. So they can be destroyed, and destroy in this, I don't mean you can destroy the state of matter entirely, but they cannot be used by us anymore. What will you do with a broken pen other than throw it into the dustbin, right? So they will be destroyed for our purposes, but they cannot be destroyed. Alright, so are they capable of diffusing into each other? Try placing a pen and a wooden stick together. Do they fuse into each other and become a wooden pen? No, they don't do that. They are not capable of diffusing into each other. Try compressing them. Take this piece of wooden stick. Put both hands on each side of the stick and press it. Does that wooden stick become a sheet of wood? It does not. Unless you put it in a machine, it is not compressible. Okay, so all these are examples of solids here. They have a definite shape, they have distinct boundaries, and they have fixed volumes. They have negligible compressibility. So in the piece of wooden stick, and if you take a book, if there is a book of 500 pages, let's say, and you press it together, it will compress for a while, but once you remove the force, it will come back to its original position. So it has negligible compressibility. If you press it, it won't stay there until the next time you pick it up and expand it again. That's not going to happen with a book. That's not going to happen with almost any other solid. So it has negligible compressibility. And they have a tendency to maintain their shape. Now this is very important because liquids and gases don't do that. If you have a table and you put a book on it, your book won't flow away like water, like I said before. It won't flow away like water. You put a book on a table, you finish your whole, at the end of the day you come back, the book is still there if nobody else touched it. The book will still be there as a book with 500 pages in it. Alright, so they maintain their shape, and even when you're subjected to outside force, even if you put it in the sun, your book is not going to melt, your book is not going to boil, it's going to remain a book. I know it will get hotter if you're putting it in the sun during summers, but nothing is going to happen to its shape. It won't melt, it won't become softer, nothing is going to happen. It will stay a book with 500 pages. Alright, they might break under force, like if you take a pen, if you hammer it, or if you throw it down, or if you and your sibling pull it apart from each other, it might break. It will break under a certain force, but it is difficult to change their shape, so they are rigid. You cannot make a pen, a rectangular pen into a circular pen. You cannot do that no matter how much force you apply. So they are rigid. You cannot make a piece of wooden stick into a wheel. You can't do that, so they are rigid. What about a rubber band? So these are a few exceptions. I am going to write EXC for exceptions. Rubber band is a solid based on what we saw because they have tightly packed particles, but they can be pulled on stretching. They change their shape. So if you hold a rubber band and if you pull it, a rubber band that was like this might become like that, right? And then when you release it back, it goes back to its original shape. If you didn't do too much damage, then it will go back to its original shape. That means the shape change, but that does not make it fall under liquids or gases. It is still a solid, but it is just an exception. What about sugar and salt? When kept in different jars, they take the shape of the jar. Are they solid? So now we are talking about a handful of sugar or a handful of salt. We are not talking about one crystal of salt or one crystal of sugar. If you take many, so if you want to consider like that, a ball, that's definitely a solid. You can't compress it, you can't, it has a definite volume, it has a definite shape. But when you take, let's say 20 balls, and if you put it in a deep pit, it will take the shape of the pit. It won't take the shape of a pyramid, it will take the shape of a pit. But that doesn't make the balls liquids or gases. They are still solids, and when you consider one of them as a single unit, they exhibit the properties of solids. So that is why they are solids too. Just like sugar and salt, they are solids. What about a sponge? It is a solid, yet we are able to compress it. So if it is when a sponge is able to sit on a table for a whole day without flowing away, without melting, without boiling under the sun, that makes it solid, but only partially. What about its volume? It does have constant volume. Volume doesn't change. The shape doesn't change unless we put a lot of force on it. And if it is dropped, it cannot be changed to another state of matter. Cannot be changed to another state. All these properties make it solid, but just because we are able to compress it to a certain extent, that doesn't make it a liquid or a gas. Every other property of a sponge makes it solid, and the compressibility that it has is what makes it an exception in solids. That's what we're supposed to understand from this, from all the way here to here. What we're supposed to understand is that there are certain properties of solids, and if you come across a particular example that follows almost all properties of solids but has one property that does not match the properties of solids, that makes it an exception of solids. It does not make it a liquid or a gas, but it makes this particular sponge right now as an exception in the solid state. Alright, so now this explains why all these are examples of solids. And then we have another experiment that talks about liquid state, and then we have the properties of liquids now. So yeah, okay. So for liquids, we have no fixed shape. When you take a glass of water and when you take a glass and you pour water into it, this is the shape that the water takes. But if you take a cooking pot, let's say, or a pan, and you put water in that, it takes that shape. If you take a pot, if you take a pot, it takes the shape of that pot. And so it keeps changing based on the container that it is poured in, liquids. So it does not have a definite shape, but it has a definite volume. So liquids have no fixed shape, but they have fixed volume. So this is pretty important here. I'm going to put a star mark. They take up the shape of the container, like I said here. Whether it's a glass or a pan or a pot, doesn't matter. It takes the shape of the container in which it is poured. They are not rigid because they can change their shape very easily, but they can be fluid. So if you accidentally spill a glass of water, it will flow all over the table. That is one disadvantage of liquids. If you don't want it to fall on your laptops or electronics, that's where it'll definitely go. That's how so many gadgets are spoiled. Alright, so they are fluid, which is why liquids are also commonly called fluids. When you go to a doctor for because you have dehydration, they say take fluids. They don't necessarily mean take only water. It can be ORS, or it can be Glucon-D, or some other lime juice. They don't necessarily mean only water. They mean fluids, as in anything that can bring back that liquid content into your body. So this is more about the activities that we saw previously, 1.4 and 1.5, and then we're moving from liquids to gases. So gases are free particles. That's how I like to think of it. So if one particle of gas is here, the other particle is somewhere over here. And if one is over here, there is something else over here, and there's one over here. So they're very free. They have a lot of place to move about. They have they move about a lot, and they're very energetic because they have more space. For if you take the case of solids, they don't have much space to move. So how I like to think about it is, if there is a bus, I'm not a great artist, so let's just say this is a bus. If there are two buses, let's say, and one of them has many people, let's say it's going from a very popular place or going to a very popular place, it has many people, they barely have place to stand properly. And then there's this other bus that's going to the outskirts of the city, let's say. So there are very few people. They can happily sit, they can sleep, they can put their bags wherever they want. So the space they have is much more than the space they have between each other. So the movement these people have in the emptier bus is much more than the movement the people have in the bus where there is not much space. They have restricted movement here. They don't know who they're going to hit if they move their elbow. They can dance around in the bus all they want, and they might not hit anyone because of the space here. That's what I like to think of. This bus is representative of solids, and this represents gases. And that's how you can see the difference. And then there is an activity here that can show you about gases, and then this is just another better representation of solids, liquids, and gases right here. Right here. Okay, so solids, as you can see, the particles are tightly packed, very tightly packed. Liquids a little more loosely packed, and gases have a lot loosely packed. So the space is here minimum, relatively more, but less than gases, and in gases it is the maximum. Alright, so moving on. We have a few more questions. This talks about density. Arrange the following in increasing density. So density is mass per volume. Let me write that properly. Let's go back here. Alright. Density is equal to mass by volume. So if you talk about solids, they have many more particles than liquids or gases. So they have more mass per unit volume. If you divide this into 9 pieces, let us say, there is one complete particle here. That's not how it usually is, but for simplicity, there is one complete particle here per unit volume for solids. For liquids, it's a little more far apart, so it's like that. And if you make this, no, it doesn't want to listen to me. Okay, if these are made into 9 parts, yes, that's all I can do now. If they have one for every other unit volume. So there's one. So on an average, there is half of a particle per unit volume. If you take gases and if you make it 9 pieces, gases have particles that are very far apart. So there might be one here, one here, one here, one somewhere there. So there's less than half of a particle here. So the density density of solids is greater than the density of liquids, and the density of liquids is greater than the density of gases. This is a pretty important relation that you can keep in mind very easily if you remember how we came to this conclusion. Okay, so based on that, we're supposed to classify this. Air is a gas, so this has the least density. Let me write the answers to this question here. Air has the least density. Exhaust from chimneys, that is also gases, but it has a few solids suspended in it, so this might have a little more. Exhaust, let me put that as exhaust, have a little more. Honey is semi-solid, semi-liquid, so if this is what did they say? Arrange the following in order for increasing density. So there are 1, 2, 3, 4, 5, 6 and 7. So the least will be air, and then we have this, which is 6, and then we have honey, which is semi-solid, semi-liquid, which can be 4 because we have water coming up here, and then we have water, which is a liquid, so it's in the middle, and that can be 5. Chalk is solid, so this is 6. No, this is 3. This is 3. And then cotton is also solid, so that can be 2. And iron is 1, because it is solid and because it is a very dense metal. Alright, so this is done. Similarly, I want you to try all the other questions 2, 3 and 4, and then we move on to the next topic. Can matter change its state? So whenever you studied matter previously, you might have come across phase changes of matter, how matter changes from solid to liquid, liquid to gas, or gas to solid, any direction, liquid to solid, gas to liquid, solid to gas. So mostly you'll see a triangle that's somewhat like this. No, gas to solid. Okay, so you see this most often when a solid such as ice, another classic example. Ice can change to water, water can change to ice, water can change to water vapor can change to water, ice, and for solid to gas there is carbon dioxide or dry ice, which changes from solid to gas directly. That doesn't go through the liquid phase. And there are similarly gas changes from gas to solid without going through the liquid phase, and that's this direct process, these two direct processes that occur here. So then we have 2 experiments that show how ice changes from solid to liquid. From ice, here it's ice, and then here it becomes water again. So then moving on, we have melting point. This is another important definition. Melting point is an indication of the strength of the force of attraction between its particles. So if the melting point of X substance is 25 degrees Celsius, this shows the strength that is present between the particles of the substance X. It needs 25 degrees Celsius of temperature to break that force of attraction and convert it from one state of X to another state of X. Or if another substance Y has a melting point of 30 degrees Celsius, this shows that the particles of Y are closer than the particles of X. So if this is X, the particles might be like this. And if this is Y, because it has a greater melting point, its particles might be closer together. Right, so it needs more temperature to break these forces than these forces. Alright, because we learned before that interstitial forces of attraction are inversely proportional to interstitial spaces, right? So as the interstitial spaces increased here, the forces of attraction decreased. But as the spaces decreased here, the forces of attraction increased, and so the temperature that was required to break the forces of attraction also increased. So this is a question you can see on the exam. You are given two substances, and and the melting points for each substance is given, and they'll ask you which of the following has greater density. So you're supposed to find out, and you're supposed to just draw for your reference, draw how X looks, draw how Y looks. If you make 9 parts of this, there will be more particles per part in Y than in X. So the density of Y will be greater than the density of X, because the melting point of Y, since the melting point of Y was greater than the melting point of X. Instead of drawing the whole diagram and dividing it into pieces, this is a handy relation again that you can remember to answer other high-level questions as well. You don't necessarily need to have a question that says exactly this. Alright, so when a solid melts, its temperature remains the same. So where does the heat go? This is another important concept called latent heat. Latent heat, very, very important. When a solid, for simplicity, I'm just taking the example of a solid, or let's take liquid. When a liquid has particles of liquid, let's say this is water, and there is a certain force of attraction that occurs here between the time when it changes from a liquid to gas. Suppose there's a flame here. Looks more like a leaf, but this is a flame, trust me. Alright, the thread might add a little effect. Alright, so between when the state of matter changes from liquid to gas, the heat that is produced here, if you measure using a thermometer, I don't know how to draw a thermometer, but if you measure using a thermometer, you will see that at some point the temperature remains the same for a certain period of time, and that is the time when the bonds are being broken by the heat. So the bonds are broken, and this allows these particles to be free from each other, and they come out as gases. So the latent heat is the heat that is required to break the bonds that form the forces of attraction between the particles of matter. Alright, so I'm explaining all this in my own words. You need to take notes also in your own words. You can't just copy everything that I am saying. I encourage you to take your own notes as I'm explaining, or you can listen to me with full attention, and then after a concept is explained, you can pause it and write it down in your own words so that you understand the concept better, and so that you can remember the concept better, because it came from your brain to the paper. easily go from your brain to the exam paper during the day of the exam. Okay, so this diagram here, this flow chart here is pretty important. As matter changes from solid to liquid when it is heated, and it changes back from a liquid to solid when it is cooled. Similarly, a liquid changes to gas when it is heated and back into a liquid from gas when it is cooled. So there is this famous triangle that I was telling you about. Let me draw it here on the other side. So this is solid, this is liquid, this is gas. And this double arrow just means it changes from gas to liquid and in this direction, and from liquid to gas in this direction. So solid to liquid to solid in this direction, solid to liquid in this direction, solid to gas in this direction, gas to solid in this direction. Alright, so solid to liquid, when ice turns into water, that process is called melting. And when a liquid turns into solid, when water turns into ice, is freezing. Water turning into ice and water turning into vapor is just another easier way that I remember, so I don't need to get confused about the simplest of things and say liquid changing into solid is melting and lose another point. So liquid changing to gas, that is water changing to water vapor, is evaporation. Or it's vaporization. I apologize. It's vaporization. So it's turning into vapor, so it is called vaporization. And gas to liquid, that is vapor to liquid to water, is condensation. Similarly, solid to gas, let's say camphor, so camphor to the gas that's produced by camphor, that is sublimation. This. And gas to solid is deposition. So these two, especially these two, solid to gas and gas to solid, is something that you need to remember, and you need to constantly keep saying it to yourself until you are familiar with the words. Okay, so this is the famous triangle I was talking to you about previously. Alright, so we have another experiment here about camphor or ammonium chloride turning directly from solid to gas. And here you have it again. Right here, the same famous triangle pops up everywhere. Effect of pressure. So effect of pressure is another important concept that just says as you increase the pressure, if you have a piston and a cylinder and if you have gas here, as you increase the pressure, the volume decreases. So pressure increase, an increase in the pressure leads to a decrease in the volume, and that leads to an increase in the kinetic energy, because they have lesser space, so they vibrate with more energy than they would. So that is the effect of pressure. And then as we move to the next one, we have a few more questions. Conversions from Celsius scale to Fahrenheit, and from Kelvin to Fahrenheit in Celsius. So there are three formulas. They're very easy. Kelvin is degrees Celsius plus 273. So if they give you a temperature in degrees Celsius and you have to convert it into Kelvin, you add 273. And for Kelvin, there is no degree here before you write Kelvin, but for Celsius and Fahrenheit, there is a degree here. So Fahrenheit from Celsius is 9 by 5 C plus 32. Okay, and then from Fahrenheit to Celsius is 5 by 9 F minus 32. So these two are interchangeable. This is just a transposition of 5 by 9 by 5 into 5 by 9 and plus 32 into minus 32. So if you remember one of these two formulas, you will remember another one. But this is an important and commonly seen formula, Celsius to Kelvin and Kelvin to Celsius. And then we have differences between boiling. We have the introduction of evaporation. Evaporation is different from vaporization. Like I made the mistake, many of us make the mistake. We think evaporation is equal to vaporization, but it is not equal to vaporization. Those are different processes. They are very similar, yes, but they are not the same. Alright, evaporation evaporation, what differentiates evaporation from vaporization is that evaporation occurs on the surface. When you heat a beaker that has a liquid, the particles at the surface of the liquid absorb energy from the surroundings as well as from the so for evaporation there is no heat. So it is a surface phenomenon because the particles here absorb energy from the surroundings and then they break those bonds between each other that they have, they break it and they escape as gases. But vaporization, you have heat. So when there is liquid here and when there are particles of liquid, the heat evenly distributes all over the liquid. So the forces of attraction here and here and here, they're all broken by the heat that is being supplied, and it is a bulk phenomenon. So the whole water starts boiling. If you boil water, there are bubbles that come from bottom, but when water is evaporating, there are no bubbles. It just keeps leaving slowly, gradually. But for boiling, you see bubbles that come here that tell you when it's time to add Maggi into the water. That is boiling or vaporization, and this is evaporation. Alright, that is an easy way of remembering the difference too. Maggi, very handy. Alright, so factors affecting evaporation. So the factors, there are a few factors. The first one is temperature. Okay, first one is surface area according to this textbook. So surface area, I'm going to abbreviate it as SA. Surface area and evaporation are directly proportional. So evaporation is directly proportional to surface area. As you increase the surface area, the rate at which a liquid evaporates into gas increases. The second one is temperature. Evaporation is also directly proportional to temperature. As you increase the temperature of the surroundings, if it's hotter here, it absorbs the particles of liquid, absorb more energy, they break free of their bonds easier, and then they move on as gases. So that's also directly proportional. And then you have humidity. Evaporation is inversely proportional to humidity because humidity is the presence of particles in the surroundings already. And if there are more particles in the surroundings, they won't easily let these particles join them again. So the fewer the particles, the better it is the fewer the particles in the air already, the better it is for the particles in the water or the liquid to go join them. So it is inversely proportional to humidity. That's an important concept. And then wind speed. Wind speed and evaporation are directly proportional, because as wind keeps replacing these particles of air away, more particles from liquids join the air. So that's also directly proportional. And how does evaporation cause cooling? As it absorbs heat from the surroundings, it causes a drop in the temperature here. Temperature drops because it is absorbed by the particles here to break their bonds. This absorption causes a decrease in the temperature, outside temperature. And these are just questions that questions related to evaporation, that we wear cotton clothes in summer because of this reason. You can read it. And there are a few more questions here that are connected to the lesson. Try it out and discuss with your friends and see if you can answer it. And then we have extra information that talks about two other states of matter. These are two new states of matter: plasma and Bose-Einstein condensate. Plasma is the fourth state of matter. It occurs in high temperatures, extremely high. I cannot stress enough on how plasma occurs at extremely high temperature and low pressure. So extremely high temperature and extremely low pressure. That is when plasma occurs. That's when you can see plasma. I mean, you can't see, but that's when matter is classified into plasma. So that's the fourth state of matter. And the fifth state of matter is the Bose-Einstein condensate. So Bose-Einstein condensate is named so because of the two scientists who were behind this, the discovery of this other state of matter. And this occurs at extremely low temperature and high pressure. So they're basically opposites of each other. They're antagonistic to each other. Okay? Let me write here opposites. They're completely opposite to each other. Alright. And then we have all the recap points here. Go through all of these. This is a quick overview of the lesson that you can go over before the day before the exam to know what all is covered here. And I just wanted to show you the 7 basic these are just 7 quantities that are measured. 7. And the units and the symbols. Go through this. This will come in handy for you in this chapter, in the next chapters, in the chapters to come. This will be very handy. And there are a few exercises here that you can try with your friends, your teacher, or anyone else who studies with you. These are every single question has the concept behind every single question has been covered in the textbook and has therefore been covered in this video. So you can very easily solve all these problems. And I created this table to help you understand the difference between solids, liquids, and gases. Take this down, don't copy it, understand why, what happened. I explained most of them. I explained all of them actually. Go back to where I taught you if you don't understand why this happened. Liquids, I put everything as intermediate because if you compare it with solids, liquids are in many cases, like in interstitial spaces. If solids have minimum interstitial spaces, liquids have a little more than compared to solids, but a little less compared to gases. That's why I put them as intermediate. They're neither minimum nor maximum. They're always intermediate between solids and gases. Alright, this is a pretty important table as well. This covers a large part of the lesson that I just went through with you. And this is something else that I created again to make it easy for you to differentiate between evaporation and boiling. If there's a question that says evaporation, differentiate between evaporation and boiling, you can read this table. You can see what the differences are, understand them, write them in your own words, take your own notes, and then you can do well in your exam, and you can make your teachers and you can surprise your teachers by adding in extra points, like, yeah, so boiling point, I added in this point that evaporation occurs at a temperature less than the boiling point, and boiling occurs at the boiling point, because that's what it's named for, boiling point, boiling, right? And this is another important point. Vapor pressure is less than atmospheric pressure for this, but vapor pressure is equal to the atmospheric pressure for this. And we already went over this. This is a surface phenomenon, this is a bulk phenomenon. These are basic differences between evaporation and boiling, but to help you identify that evaporation is not equal to boiling, I just came up with 3 basic differences, and this is a diagram that shows that evaporation is a surface phenomenon, but boiling is a bulk phenomenon. These are the bubbles that are as a result of, let's just add a little flame to this. Yeah, okay, so that ends the lesson there, and I have a few points to recap. This is what we just did. So you can pause here, take it down, see if you understood everything here, and if you didn't understand, feel free to go back and watch it again. So we discussed about the physical nature of matter, we discussed about the states of matter, solids, liquids, and gases, properties of each state of matter. Again, pause this if you want, go through. I added in a few more. They vibrate in their positions, they have least amount of fluidity, stuff like that. I added in more than what we spoke, so pause if you want to and note it down. Make sure you understood everything. The same it's for liquids. They have a few more added points as well. And then we have gases. If only this will move, we can show you gases. Yep, okay. So that's gases. Take a screenshot or write it down, whatever. And then we have the 6 phase changes. These are 6 phase changes. We have discussed about the differences between evaporation and boiling. We discussed about latent heat. We discussed about Bose, Einstein, condensate, and plasma. We discussed related questions. We discussed units. And we covered pretty much every concept that had been covered by NCERT in this chapter. So that's all for this chapter. I hope the video helped you understand this concept better. Head on to the next video, which will cover is matter around is pure. That is the 2nd chapter in chemistry in NCERT Science 9th class. And don't forget that you can do this. Have a great rest of your day, and most importantly, don't forget to like and share this video, subscribe to our channel, and rock your exam. All the very best. Bye bye.